like the heat transfer problem that I touched at the beginning. So you've completely simplified the whole physics of the problem and just brought it back to its simplest common denominator. Okay? So that's what the test does. So basically, as I said, you have all these simplifications, and the simplifications allow me to cancel all these other times and say basically that the time to reach pyrolysis is the time to ignition. Now I can simplify the equation, it's still transient, come up with a solution to the equation, and basically look into a simple way of assessing the problem with a simple algebraic equation. I fit it to experimental data, and on the basis of experimental data, I extract the parameters that control the problem. So the experimental data is fed to the theoretical predictions, and I extract the characteristic values. Now, there's some parameters that I have evaluated for the test, but other parameters are the ones I extract. In this case, two parameters, the thermal inertia and the ignition temperature. So I have reduced the whole problem into two single things. But in the process, I've made a whole bunch of assumptions now. In the other case, I had very simple assumptions. Now I have a whole set of assumptions, of which some of them are very well assessed, some of them are not. Okay? And this is, I think, in Fire when we start getting into problems. Because the problem in itself is very complex. We have to simplify it down completely to be able to extract a set of relevant parameters. But when we start looking into the assumptions, in many cases, we run into trouble. Okay? And I think that in this particular case, the parameters are clear. There's two parameters. In my simpler case, there was only one. But here I have two. Now, if I have to assess performance then, I need to be able to establish a way in which these two parameters are going to be used in a careful manner so that I can actually say if a material is better or worse than another one, or if it actually I'm going to introduce it or not introduce it into a model. So in the case of this problem, basically this information is the backbone of the standard. It is an adequate interpretation for a relative assessment of the material. It is an adequate interpretation to extract properties for fire modeling. These are the two questions that need to be answered. Now, my simplifications, in this case, resulted in one important problem. And the important problem is that the truth is that K rho C and T ignition are not material properties. They are material properties biased by the environmental conditions of the standard. Now, the environmental conditions of the standard have been created in a very careful manner, so that they not only represent a well-defined set of boundary conditions, but also in a way such that a well-defined set of boundary conditions is somehow representative of a fire scenario. Okay? So as a relative assessment of the material, it is actually pretty good, because the assumptions themselves are fundamentally all solid up to the point where I make a relative assessment. But if I now want to use these properties and input them into a complex, detailed fire model, then it fails, because those properties include some parameters that are linked to the environmental conditions of the standard, which are not going to be the same as the ones of the fire. So by misusing the properties, we are ruining the standard. So the questions that come up is, does the analysis has to be so simple? And do you have to come up with an analytical formulation? Not necessarily. I can do a very complicated numerical solution of a solid and try to extract more details. But the problem is that you're going to end up with a lot more parameters and a lot more complications to the problem. Do we need to make all the assumptions? Well, it's not necessarily the case. And what is the error introducing all the assumptions? That is probably the question that remains always unanswered. So some of the assumptions have been looked into some detail. There's three which are the main ones, have been looked into quite a bit of detail, and there's numerous studies that have tried to assess this. Now, the answer is not very clear. I think the first two can be really taken in a quite solid manner. The third one is the one that is very tricky. So, the question is this a good standard? Well, these two parameters have been shown to depend on the environmental conditions, but they are the properties governing ignition. They are. They are the key properties that are going to govern ignition. But the standard operates under relevant environmental conditions. So the two things are actually validating the fact that these two properties are actually quite useful as a way to assess performance for ignition. It's a good relative standard. not a good standard to deliver properties from all. So at the end of the day, basically a good standard for me delivers the relevant parameters. It does not compound parameters that have independent influence on the process. In this case, we have compounded K, rho, and C and put them together because they appear together as being the relevant parameter. But if I try to compound K, rho, C, and T ignition into one single parameter, then I am mixing two things that are actually very separated in the whole process of ignition. So I cannot compound the two into one single index. I need to have the two independent things because they are two completely different things. So for me, a good standard is based on a method that minimizes error. And in a way, I don't believe that it necessarily has to mimic reality. And I think that's one of the mistakes that we always make. We try to force our standards to mimic reality. I think all that they have to do is to be, if the environmental variables are going to affect the parameters that I'm extracting, we have to be within the range of the conditions of the real application. But we do not have to mimic the reality. Thank you.